The reactions of alkynes are very similar to alkenes. And so what we're going to find in chapter 9 for alkynes is that we've covered a lot of the reactions and potentially some of the syntheses of alkynes back in chapter 8 when we talked specifically about the alkene reactions. The difference is that an alkyne has two pi bonds, and so with alkenes, we reacted HX, H plus H2O, hydrogen, a bunch of other reagents with the double bond. Now I have two pi bonds, so I'm going to be able to react twice as much stuff. Now, there are a couple reactions that are different for alkynes versus alkenes, and we'll get to those. So alkynes are hydrocarbons that contain carbon-carbon triple bonds. And the simplest alkyne is actually this molecule called acetylene. Acetylene, which is C2H4 or C2H2, is a gas at room temperature, and it's a fairly flammable gas. Acetylene is used to produce flames that are very, very hot, so it's used in welding and some other applications. It's been around for a long time and been used for a long time. You can actually get acetylene from taking a mineral called calcium carbide and reacting it with water, and it will actually produce the acetylene. The calcium carbide actually has two deprotonated carbons in it, so this is the structure of the C2 minus C2 2 minus species. What happens is that these C minus bases deprotonate the water, and you form the acetylene gas. This picture is just one I found on the web that has calcium carbide. They put an ice cube on top of it and then actually lit it on fire, because what's happening is as the water melts, it produces or it reacts with the calcium carbide to make acetylene, and that acetylene then burns in the air. So the coal miners used to use this in their hats. They used to put a piece of calcium carbide there and then add a drop of water and light it to produce like the little helmet lamps. That was a long time ago, but calcium carbide historically has been around for a very long time. The last thing about alkynes generally is that they have a formula of CnH2n-2. And what that means is that we basically have, if we went back and calculated degrees of unsaturation that we used for alkenes, we actually have 2 degrees of unsaturation. And that corresponds to 2 pi bonds. So it's not saturated, it is an unsaturated hydrocarbon. So in terms of naming the alkynes, it's pretty straightforward and very similar to naming alkenes. We do not have cis-trans isomers or EZ isomers in carbon-carbon triple bonds because there's only 2 groups that can be attached to the carbon-carbon triple bond, and with the linear geometry, there's no possible geometric isomer. So we pretty much just have the naming systems that we used for alkenes now changed to a YNE suffix. So the rules are pretty much the same. You locate the longest continuous carbon chain in the molecule, you number from the end closest to the carbon-carbon triple bond, and then you name, number, and alphabetize the substituents. And then when writing the name, you're now going to have the number of the carbon-carbon triple bond, the parent name, followed by the YNE suffix. And so, for instance, if we had something like this, we would look at the longest continuous carbon chain. So this is going to be a pentyne. It's a 5-carbon chain. The YNE indicates that there is a triple bond in that longest chain. Numbering from the end closest to the triple bond, we would number from right to left. So 1, 2, 3, and 4, 5. and we would call this then 2-pentyne. So just like for alkenes, the number before the parent name and the suffix tells you where the triple bond is. So in this case, 2-pentyne means the triple bond is between carbons 2 and 3. Again, the numbering scheme takes priority. So if I was to have something like this, we would have to number at the end closest to the triple bond. So we'd have 1, 2, 3, 4. So this would be 4-chloro, 1-butyne would be its name. Okay, so naming alkynes is pretty similar to naming alkenes, except we don't have to worry about having cis, trans, or easy prefixes to worry about. Now, that does raise an issue that sometimes we have to name molecules with multiple functional groups. And what we've seen so far is that when I put a double bond in the molecule, the double bond took priority in terms of the numbering scheme. And also the number that came before the parent name and the suffix was the number of that, in this case, those cases, double bonds. And so just in general, when you have more than one functional group in the molecule, the one that has the highest priority is the same one you would get in your Con-Ingold pre-log sequence rules. And so if I was comparing, for instance, a molecule that had a double or a triple bond in the molecule, the triple bond would take priority because the triple bond would have priority in our Con-Ingold pre-log sequence rules. And number two, that functional group then is given the last suffix in the parent name and also given priority when numbering the longest continuous carbon chain. So you just have to be aware that as we go through some of the other functional groups next semester, that as we name multiple functional group containing molecules, that the one with the highest Con-Ingold pre-log sequence rules will be the ones that come that we have to number closest to the beginning of the chain, and also that come at the end of the naming. So in terms of structure and bonding of alkynes, this takes us back all the way to the beginning of the semester. A carbon, if you think about a carbon-carbon triple bond of, let's say, acetylene, this carbon is sp hybridized of carbon-carbon triple bonds, double bonds, and single bonds. The triple bond has the shortest carbon-carbon bond. You can either explain that because between these two carbons there's 6 electrons, and that's pulling the nuclei together. That's how many electrons are being shared. Or you can think of this in terms of sp has a 50% s character, and the higher the percent s character that you have, the shorter and more difficult to break the bond becomes. There's 2 pi bonds and 1 sigma bond. This has a linear VSEPR geometry, and since it has 2 pi bonds, it can act as a nucleophile, not just as a nucleophile once, but as a nucleophile twice. And so each one of the pi bonds can actually react with an electrophile. So we'll see that a lot of the reactions of alkynes are similar to the reactions of alkenes, except they can occur twice. So going back, remember that we formed our sp hybridization by mixing the s and the p. That gave us 2 sp hybrid orbitals and 2 unhybridized p's. So we formed the triple bond by overlapping the 2 sp hybrid orbitals, and then that gave us 2 unhybridized p's that we could go ahead and sideways overlap to give us the 2 pi bonds. And so we've got our top and bottom lobes of the first pi bond, and then the second one's in and out of the plane of the paper. So the structure of acetylene then is linear, and there's no geometric isomers possible for a carbon-carbon triple bond. In double bonds, we did have cis, trans, or easy structural isomers that were, or I guess geometric or stereoisomers that were possible. What about the stability of alkynes? Well, in terms of the stability of alkynes, the first thing that you would want to realize is that with the two pi bonds and the sigma bond, the carbon-carbon bond is the carbon-carbon triple bond is the shortest of the bonds, but it also has the greatest bond dissociation energy because it is the shortest bond and there is the most number of shared electrons. So if you wanted to break a carbon-carbon triple bond, you're going to have to break the pi bond first, a second pi bond, and then finally break the sigma bond. And so its bond dissociation energy is going to be much higher than for a carbon-carbon double bond. Now, in terms of the alkynes, you could measure the stability of alkynes in the same way that we did for alkenes by comparing the heats of formation and heats of combustion. Now, remember that when we talked about the stability of alkenes and the number of alkyl groups, what I did was I showed you a diagram where we could plot out basically the energy, and then what we did was we added hydrogen and palladium and platinum, the reaction we just learned on Monday, and that then reduced that molecule down to the alkane. And that gave us what we call a delta H of hydrogenation. And if we did that with different alkenes, what we would do is get different heats of hydrogenation, and these were all exothermic reactions because they were all negative in sign, so that the adding hydrogen to a double bond produced energy to give us a carbon-carbon single bond. So what we did was, by comparing the heats of hydrogenation, the one with the most negative heat of hydrogenation turned out to actually be the least stable, because since they all go to the same product, our delta H here is larger numerically, or larger negative, than this one over here, and so the smaller the heat of hydrogenation, or the less exothermic it is, the more stable the molecule is. And if I go back and say that again, the less exothermic the heat of hydrogenation, the more stable the molecule is. And so that kind of fits our general theme of reactivity versus stability. So the more energy you get out of hydrogenating the alkene, the less stable it is. The less energy you get out, i.e. the less reactive the double bond, the more stable it is. So you could do this same thing for the triple bonds, and you could probably do heats of hydrogenation as well, and we'll learn about those reactions on Friday. But if we look at this, we can actually do this another way, and people will sometimes do heats of combustion. So remember that for an alkane or an alkyne, when you react these with oxygen gas, that's a combustion reaction and you form carbon dioxide and water. So you could do this same sort of analysis to determine the stabilities of molecules by doing heats of combustion. And again, here the delta H of combustion is going to be negative because these are all exothermic reactions. And so if you had, for instance, let's say this alkyne, and I'm going to change this and make it butane. So there's 4 carbons there. If you compared butane versus, well, 2-butane versus 1-butane, which one of these two molecules would you think would be the most stable? Well, if you didn't know, we could compare these two by reacting both with oxygen gas and doing combustion. And since these are both exothermic reactions, and since both molecular formulas are the same, they're going to produce the same number of molecules of carbon dioxide and the same number of molecules of water. So our products then are going to have the same energy level. Okay. And so the question is, which one has the greatest, or the greater delta, the greater negative heat of combustion? And then that would tell us which one of these two molecules is more or less stable. Now, can you make a guess as to which one of these two alkynes is the most stable based on the carbon-carbon triple bond number of substituents? And what I'm asking here is there any parallel between the stability of alkynes and the stability of alkenes? What do we know about alkenes? The more substituted, the more stable. So this alkyne has two alkyl groups attached to a triple bond. This alkyne only has one. And so it turns out that this one is more stable than one butyne. And the reason is that a carbon-carbon triple bond also likes to get electron density, so that when you attach an alkyl group, remember that your carbons become slightly positive, or hydrogens become slightly positive, your carbon slightly negative, so it can now push electron density into that carbon-carbon triple bond. And the more alkyl groups to push electron density, the more stable the triple bond. So it's exactly the same argument that we made for alkenes. So if I go back here, internal alkenes, and they shouldn't be alkenes, they should be Ys. It's a typo. Internal alkynes, which have the triple bond in between alkyl groups, turn out to be more stable than terminal alkynes, which have the alkyne, the CC triple bond at the end of the chain. So internal alkynes are more stable. Well, these are just simply more substituted. So just like alkenes, more substituted to triple bond, the more stable the alkyne. Okay. Now, another important property of an alkyne, and this is only an important property for the terminal alkyne, is it turns out that the hydrogen attached to the end of the carbon-carbon triple bond, this is the way I type out the carbon-carbon triple bond, that hydrogen at the end of a terminal alkyne is acidic. And it has a pKa of about 10 to the 26th. Now, measuring pKa's of organic molecules is difficult because we're no longer measuring the pKa's of these in the solvent water. Everything you did in general chemistry was measuring a pKa or a pH in water, but organic molecules don't dissolve in water, and a lot of times they are less acidic than water. So pKa's above 16 are routine, okay? Or above 14, sorry. When you think about water ionizing to form hydroxide and hydronium, the Ka of that equilibrium, remember, is 10 to the minus 14th. So if we look at this alkyne, its pKa is a lot higher than, or its pKa, which would correspond to a Ka of 10 to the minus 26th. Its Ka is a lot smaller than the Ka of water, which means that this is a pretty weak acid. Now, if you took a carbon-hydrogen bond of methane, you would find that it has a pKa of 60, which means its Ka is 10 to the minus 60th. An NH bond has a pKa of 40, which means its Ka would be 10 to the minus 40th. And water, of course, has a Ka of 10 to the minus 16th. So on the periodic table, when we talk about a CH being less acidic than NH, less acidic than OH, as we go across the periodic table from left to right, these are kind of the quantitative numbers that go with that. Why does anybody care about these? Well, that's a good question. But the reason that we care about how acidic the carbon-hydrogen bond is in the alkyne is that if I could deprotonate this alkyne, I could make what's called an alkynyl anion. And that alkynyl anion would allow me then to take this anion and I could do substitution reactions with it. I could do SN2 and I could form new carbon-carbon bonds. The problem is, what base would I need to use to completely deprotonate something that has a Ka of only 10 to the minus 40th? Or no, sorry, not 40th. 10 to the minus 26th. Well, it turns out that of these bases, the water and hydroxide won't deprotonate this carbon-hydrogen bond. The only thing that'll deprotonate this is something that has a base whose conjugate acid is weaker than the conjugate acid of the alkyne. And so it turns out that if I have a deprotonated NH3, NH2 minus, that would completely deprotonate. That would completely deprotonate the alkyne, the alkynyl hydrogen. And so would something like CH3 minus. That would also completely deprotonate. Well, we'll talk about how to make C minuses next semester in the second semester course. We've already used NH2 minus to use this as a base for E2 eliminations. So it turns out that we're going to use NH2 minus to deprotonate terminal alkynes to make alkynyl anions, because they're a sufficiently strong base to completely deprotonate the alkynyl hydrogen. Okay. Now tertiary butoxide, on the other hand, tertiary butoxide won't deprotonate. That won't deprotonate a carbon-carbon triple bond. So only NH2 minus is going to be the base that we use. So if I wanted to take an alkyne, a terminal alkyne, I could react it with NH2 minus. That would come in and deprotonate the hydrogen and would now let me make my alkynyl anion that I could now use as either a nucleophile, or I suppose I could also use it as a base. The problem in general is the stronger the base, the stronger it is as a nucleophile. So these can be used as either nucleophiles or bases depending on the molecules they react with. Well, one of the things that I can do is I can react primary and secondary alkyl halides with alkynyl anions, and they'll undergo SN2 reactions. So if I had an alkyne like this one propyne, I could add an alkyl group to the right side of the molecule if I simply deprotonated that terminal hydrogen and then took the propyne, or the propynyl anion, and reacted it with something like, I don't know, a primary alkyl halide. So here I have a primary alkyl halide reacting with a strong nucleophile. So what would happen is the nucleophile would come in, kick off the leaving group. That reaction would be SN2. And I would end up adding the the alkyl group to the other side of the alkyne. So this ethyl group is what I would add to the alkynyl anion. And this is just simply an SN2 reaction. I would also get Cl minus. Okay. So this reaction is what's called alkylation. An alkylation reaction is any time you add an alkyl group to your molecule. In this case, I'm doing it by making a strong nucleophile, reacting it with a primary alkyl halide to give us this basically alkylated alkyne through an SN2 reaction. So we can basically alkylate our alkynyl anions and add an alkyl group to a triple bond. Now, what we've done so far this semester and will continue next semester in doing is basically when we talk about a new functional group, we'll talk about naming and physical properties and all of that stuff. And then we'll talk about how to prepare that functional group. This actually turns out to be classified by your book of a preparation of an alkyne, but it's kind of cheating because in order to make these alkylated alkynes, you needed to start with an alkyne. And we'll talk about how to make the triple bond here in a minute, but these are also considered to be preparations of alkynes. So here's a problem. This is the problem I sort of just did. So if we take an alkynyl anion and we react it with either primary or secondary alkyl halide, we're going to do our SN2 reaction and we're going to end up then adding the alkyl group to the carbon-carbon triple bond. So if you wanted to convert acetylene into this, what is this, 2-pentyne, how would you do it? Well, what you'd have to do is first treat the acetylene with one equivalent of the NH2 minus, and that would form this anion. You could react that with, let's just react it with methyl chloride. We would do an SN2 reaction, and that would then alkylate one side of the carbon-carbon triple bond with a methyl group. And I'm going to do this backwards, but that's okay. So then what I could do is then I could treat this with another NH2 minus base and form the anion on the other side of the alkyne, and now react that with ethyl chloride, and this would again do another SN2 reaction to then give us alkyl groups, the ethyl on one side of the triple bond and the methyl group on the other side of the triple bond. So this is a way to convert a terminal alkyne into an internal alkyne by adding any alkyl group you want to that end of the carbon-carbon triple bond. Well, maybe not every group to the triple bond. The restriction on this reaction is that you could only use primary and secondary halides because we want to have this reaction go by SN2. What happens if I was to take an alkynyl anion and I was to try and react this with a tertiary halide? What do you think would happen in this reaction? Well, the reaction, this is a strong nucleophile. We know that. But the problem here is that strong nucleophiles are also strong bases. And so what happens when you react a strong base with a tertiary alkyl halide? This reaction cannot go SN2, right? Because this carbon's too sterically hindered to have an SN2 reaction occur. So what happens is that typically strong nucleophiles, when they can't act as nucleophiles, turn around and become bases. So this base would actually do an E2 reaction on our alkyl halide. And so if we tried to do this reaction, we would actually have this with a tertiary halide undergo E2, which means we'd have to find our alpha carbon and then our beta carbons. And we'd have to see that our beta carbons have beta hydrogens. So here would be a beta hydrogen. So what would happen? The base would come in, now grab that hydrogen, have this pair of electrons move here, and kick off the chlorine, so that what I would end up forming is I would protonate my base, but then I would also form an alkene. Okay, so the double bond would form between, let's say, carbon 1 and carbon 2 here. Okay, so the key thing to remember about trying to alkylate alkynyl anions is primary and secondary are okay because that goes by an SN2 mechanism. The problem is when you try and alkylate an alkynyl anion using a tertiary alkyl halide, you're going to get E2 instead of SN2. Now you might say, okay, I get the E2, but is this sterically hindered strong base, or is this a small strong base? And I would consider the alkyne to actually be a small strong base, and so I would consider it to be the equivalent of our NH2 minus, so that if I gave you an alkene or an alkyl halide that had more than one possible product, the major product of the reaction I would predict would be the one that's more substituted, because this alkynyl anion is actually able to get to both hydrogens, whether they're sterically hindered or not, in order to get then the more substituted alkene, just like an NH2 minus would. So if you try and do a tertiary alkyl halide try and alkylate that with an alkynyl anion, or alkylate the alkynyl anion with it, you're going to get E2, and the product, I would consider the major product of that reaction to be the same as if you used NH2 minus. Okay. So that's one way to prepare an alkyne, is to take a terminal alkyne, deprotonate it, and alkylate it. But like I said, that's kind of cheating because we're starting with a triple bond to make a triple bond. Now, something else you can do with alkynes or alkynyl anions is what are called acylation reactions. And we're going to talk about acylation reactions a lot more next semester. But I do throw it in here. When you have a carbon-oxygen double bond, we know that the oxygen is slightly negative and the carbon is slightly positive from the polar covalent bond of the carbon. Not only that, but it turns out that there's two resonance structures for a carbonyl. I could move this pair of electrons up to the oxygen and actually make okay, what's going on? I could have this resonance structure be formed. Now, if you go all the way back to the beginning of the semester, you'd say, well, that's not very stable because the carbon doesn't have a fulfilled octet. You're correct. But the idea here is that these two resonance structures, this carbon has a slightly positive charge and the oxygen slightly negative. Now, the oxygen of the carbonyl can be protonated with acid. But the carbon of the carbonyl is slightly positive, and so it's an electrophile. And so what can happen is if we look at the alkynyl anion as a nucleophile, it can actually react with the carbonyl in a nucleophile electrophile reaction. So if I come down here with my alkynyl anion, what can actually happen is it can take its pair of electrons and form a carbon-carbon bond to the carbonyl carbon. But if I stop here, I'm going to get five bonds to a carbon. So at the same time this carbon donates a pair to the carbonyl carbon, the CO bond has to break and the pair of electrons have to go to the oxygen. And so what I end up doing is I end up forming a carbon-carbon bond and then the alkoxide ion. Okay. So this carbanion attacks the carbonyl carbon as the electrophile pair of electrons moves to the oxygen, and I form my alkoxide ion. Well, if you form your alkoxide ion, then what happens is that after that reaction's over, we then usually add H plus to the mixture, and the H plus then protonates the alkoxide so that what I end up doing is forming an alcohol as my final product. So this reaction where in essence I'm adding a carbonyl group to the alkynyl anion is what's called acylation, because this carbonyl is sometimes called an acyl group. And so when you do this reaction, what you end up doing is you end up forming the alcohol, and this was our carbon that was in our carbonyl. So if we look at these two parts of the reaction, and I'll color code them, this part, the blue part here, ends up over here. And so I've added that carbonyl group to the triple bond, but now it becomes an alcohol. Okay, so sometimes we'll acylate the carbon-carbon triple bonds, the alkynyl anions, to make an alcohol. And we'll see this reaction a lot next semester because we're going to take lots of C- species and add them to carbonyl groups. And every time we do that, we'll make an alcohol. Okay. So last issue with alkynes that I'll go over in this lecture, and then we'll talk about reactions of alkynes on Friday, because a lot of the reactions of alkynes are basically the same reactions that we had for alkenes. So if you know reactions of alkenes, you'll know the reactions of alkynes. But how do you prepare alkynes? And not just this, oh, well, let me take one triple bond and convert it to another triple bond. How do you make the triple bond from scratch? Well, what we end up having to think about is doing what we would call a double E2 elimination. So we know that to do E2s, you need a carbon, an alpha carbon with a leaving group, and you need a beta carbon with a beta hydrogen. And then you're going to eliminate HX as the base. Basically, the base will come in, take off the beta hydrogen, pair of electrons moves, and halogen gets kicked off. And actually, I shouldn't put that. I should actually do this to give some semblance of reality to the antiperiplanar geometry. So if I do that once, I get a double bond. Well, what if I have two leaving groups attached to the same carbon? Then I could do that one time, and I could make that molecule, that double bond. But then what if I took that same base, or a stronger base, came in and deprotonated the hydrogen attached to the carbon-carbon double bond? Couldn't I then do a second E2 and now form the carbon-carbon triple bond? Well, the way I've shown you is the way to do this double E2 elimination using what's called a geminal or a gem dihalide. So the geminal term means that the two groups are attached to the same carbon. And so if you had a geminal dihalide and you had a beta carbon with two beta hydrogens attached to it, you could use a base to do the first deprotonate or to the first E2 elimination, and then use a second molecule of base to do the second E2 elimination. So there's a number of issues here. First, what bases would I use? Well, we know that the bases that we used for forming a double bond were NH2- and tertiary butoxide. Now, for this reaction, I would actually just use an NH2- as my base, because then it's strong enough to actually deprotonate the hydrogen from a carbon-carbon double bond. And so in this case, we would use two equivalents of NH2- in order to do this double E2 elimination, and therefore form the carbon-carbon triple bond. So that's how we could prepare a triple bond from a geminal dihalide. Well, you don't have to always use a geminal dihalide to do the elimination reaction. If I start with this middle reaction, here is my vicinal dibromide. And so vicinal dibromide means that the bromines are attached to adjacent carbons. Well, what if I use two equivalents of NH2- on this molecule and did a double E2 elimination? So maybe I would have my NH2- do what? It would come in and it would grab this hydrogen, pair of electrons moves down here, bromine gets kicked off. Okay, if you're having a fit, I didn't show it as the antiperiplanar geometry. It would have to form the antiperiplanar geometry. I'm just not showing that in this particular molecule. So I would do my first elimination, and that would make my alkene. Then let's say I do a second elimination where the NH2- comes in, grabs that hydrogen, pair of electrons moves there, leaving groups leaves to give me the carbon-carbon triple bond. So I could do doubly 2 eliminations on vicinal dibromides, is the point here. I can do them on geminal dibromides, and I can do them on vicinal dibromides. But here's the problem. The problem is that I don't know how to make geminal dihalides. You will on Friday, but you don't right now. And the other problem with geminal dihalides is we normally make those from triple bonds. So I'm going to make a triple bond after I've used a triple bond to make my original molecule. Not likely to happen. But I do know how to make vicinal dibromides. How do I make vicinal dibromides? By reacting bromine with alkenes. And when I add bromine to alkene, what happens? The bromides add trans, and when they add trans to each other, that means the hydrogens now are going to be set up in a perfect position to actually double eliminate through the antiperiplanar geometry. So I can start with an alkene, react it with bromine, form a vicinal dibromide, do double E2 elimination to give me a carbon-carbon triple bond. And so that's how we can synthesize the alkynes from a molecule of vicinal dibromide that I know how to make from the alkene. On Friday, we'll learn how to make the geminal dihalides, and in theory, I can do the same double elimination reaction here. Okay? So just as a practical example, let's say I started with this alkene, and I reacted it with Br2. So I would make this molecule when I do my bromination. And now if I treated this with the first equivalent of NH2 minus, what'll happen is that'll come in, remove that hydrogen, pair of electrons moves here, bromine gets kicked off. To form the, what is this? This is the Z form of this double bond. And it has to be the Z form, at least in this case, because then my second equivalent of NH2 minus would come in, grab that hydrogen, pair of electrons moves there, and then the bromine gets kicked out so that I could form my final product, which would now have the carbon-carbon triple bond. Okay. Now, the more challenging question would be, how did I make this double bond? And we won't worry about that for the time being, although I may come back to that question on Wednesday in class. Okay, so this is the first, these are the introductory ideas about alkynes, and then the preparations of alkynes, both in terms of doing alkylation reactions by alkylating the alkynyl anions. Another reaction you can do with alkynyl anions, namely an acylation reaction. And then how do you prepare alkynes directly? Well, you prepare alkynes from either geminal dihalides or vicinal dibromides. Okay, so that's the beginning of alkynes, and there's really, I mean, there's some newer stuff here, but a lot of this at this point is kind of reviewing what we did to make double bonds, as well as what you'll find on Friday is a lot of review in terms of making, of reacting the triple bond, because all it has is 2 pi bonds, and we react the same way that we react double bonds, except we got twice as much reactions that we can do. Okay, so I will post an online quiz for Wednesday. You will also have an in-class quiz on Wednesday over writing the products of the reactions, the alkene reactions that we talked about on Monday, writing the major products, and there will be a homework assignment or a homework set of problems online, well, sometime on Monday.